Tyrannosaurus Rex, the most terrifying creature that ever stalked the planet.
It's something that seems as if it could come from a nightmare.
Horrible, terrifying monsters that were actually real.
It's a cultural icon, the poster boy of the dinosaurs. But for years, we got it completely wrong.
This animal's a lot more complex and a lot more sophisticated than you ever could have imagined.
Now, a band of pioneering experts are revolutionizing our understanding of this infamous predator, aiming to recreate the most authentic T-Rex ever.
We can really look at T-Rex in a way that we never could before. Its secrets are now being revealed.
They're uncovering the bone-crushing power of its jaws.
That's T-Rex bite force right there.
Testing his top speed, getting inside his mind, and asking what it really looked like.
This is an animal that is so awesome in so many ways.
They're reimagining and rebuilding T-Rex to bring it back to life. Badlands on the Alberta-US border stretch across hundreds of miles. This barren landscape holds hidden treasure because this is ground zero for Tyrannosaurus Rex. Paleontologist Phil Curry has worked these hills for years.
The Badlands are very significant because basically we have the last 10 million years of dinosaurian history represented here. And we have sites that are incredibly wealthy with dinosaur material. They show us what's happening over a unit of time that we consider one of the most important, the period leading up to the extinction of most dinosaurs.
This was the Cretaceous period, when the great dinosaurs who walked the Earth were the most evolved and complex of their kind. The dominance of the dinosaurs came to a sudden end 65 million years ago, when the catastrophic impact of a giant meteorite changed our planet forever. Across the US border, Badland paleontologist Greg Wilson is digging into these Cretaceous rocks, exposing the fossilized remains of the dinosaurs that populated that ancient world.
This area here would have been a fairly lush coastal lowland environment with a very rich diversity of animals, from insects and lizards and frogs to Triceratops to Ankylosaurus and duck-billed dinosaurs. These guys would have been like cows on this landscape, and they preserved well in the fossil record.
Mostly, the diggers find the remains of these plentiful herbivores. But sometimes, they uncover the fossilized bones of the creature that preyed upon them. The apex predator of the Cretaceous, Tyrannosaurus Rex.
Something that's quite surprising is the fact that there aren't that many complete T-Rex that are known in the world. Somewhere on the order of 25 specimens that have a decent number of the elements of the skeleton of a T-Rex.
Recently, Badland paleontologists discovered one of the best ever. Here in the Museum of Natural Science in Berlin, Germany, it's now housed in a private room. They call it Tristan. 4 meters high at the hip, over 12 meters head to tail, and an enormous skull filled with some of the largest teeth ever seen.
Tyrannosaurus Rex is really one of the most remarkable animals you could ever imagine. It's just one of those animals that's mythical in its gigantic splendor. But this is an animal that, in some ways, has had a bad rap, because it's a dinosaur that's considered to be a brainless killing machine.
For decades, T-Rex was thought to be a monstrous, mindless, tail-dragging, cold-blooded lizard. Today, scientists are studying living animals and using the very latest technology to overthrow these outdated myths.
The amazing when you actually start studying it and you realize that this animal's a lot more complex and a lot more sophisticated than you ever could have imagined.
Driven by the science, we're going to put flesh back on Tristan's bones, creating the most authentic T-Rex in over 65 million years. Tristan's skeleton provides our first clue. Evidence of tiny tendon markings allow us to reconstruct the scale and true detail of his complex musculature. The patterns of these muscles are helping scientists to answer a basic question. Just what kind of animal was he? The Alabama swamplands, home to some real old-timers. The ancestors of these giant reptiles coexisted with the giant dinosaurs. Their body structure appears similar. So just how reptilian was T-Rex? Naturalist Chris Packham and paleontologist Greg Erickson are tackling this question by exploring what alligators can teach us about the raw power of T-Rex's bite.
To understand dinosaur paleobiology, we need to understand the biology of living animals. I used basically the data from these living animals as sort of a time machine to go back and try to understand what animals such as Tyrannosaurus rex were doing.
Typically, we look at mammals, we see that the muscles are on the outside of the skull. What's interesting with the crocodilians is that the muscles, like T-Rex, are on the inside of the skull. And they're huge and they're powerful. And the way that they articulate that jawbone means that they can generate an enormous pressure.
Head up. 1, 2, 3. Got roll.
Greg's team are masters in trapping alligators without harming them. But this job is not for the faint-hearted. Greg has brought along his favorite tool.
Well, I call it Dragon Slayer, but it's a bite force meter. So I'll tell you what, I'm gonna go ahead and test the bite.
I'll do the reading.
Fantastic.
Set this down there.
Ready?
Yeah, yeah. Oh, yeah.
What do we get?
2,058 pounds.
Wow, over a ton of bite force.
That's a pressure equivalent to the weight of a water buffalo. T-Rex had very similar jaw muscles. So Greg scales up to calculate the downward force the dinosaur could generate.
With T-Rex, we estimate bite forces of 8,000 pounds.
8,000?
Yeah.
That's a crushing bite of an enormous magnitude.
It's mind-boggling to think about.
That's 4 tons of pressure, like being squashed by an elephant. This is the skull of a cow, a modern analogy for T-Rex prey, a giant herbivore. The team uses an impact generator to recreate the power of T-Rex's bite.
$550, $600, $1,500. Wow. Oh, Greg. Oh, dear, oh, dear.
That's T-Rex bite force right there. Look at the carnage.
Yeah. So basically, that's bone that's endured the bite force of T-Rex. I mean, basically, this is just dust, isn't it?
Isn't that amazing?
Nothing survives the bite of T-Rex, does it?
Oh, T-Rex was the ultimate killing machine, in my opinion.
But T-Rex was a killing machine with very strange teeth. With his monstrous reputation, you'd expect a set of deadly daggers. But surprisingly, they're of a uniquely odd design.
There's more than meets the eye here. These are the largest teeth of any dinosaur, and they're actually quite blunt. It's sort of like a railroad spike, or some of my colleagues call them lethal bananas, and it's kind of what it's shaped like, a banana. They're very dull on the tip, but one of the secrets is that this animal has a serration row called a carinae on the front and the back here. The bones would literally explode when T-Rex made a very forceful bite.
So, just how much damage can a banana do? A bronze cast stands in for an actual T-Rex tooth.
Go.
Wow.
Wow.
T-Rex bites again. Wow.
Destroyed. You can see where it initially entered there, Greg. So it made a hole, didn't it?
Yeah, it's like a hot knife going through butter at first, but then it basically introduced a crack where the serration heads or carinae is, and split the bone apart.
And that was those ridged edges, the carinae.
You could imagine how it could easily have done this to much larger bones. Maybe even bones from a large duck-billed dinosaur, or even Triceratops. It's amazing, isn't it?
It's amazing.
So, what does T-Rex's bite tell us about his origins? Tristan's jaw muscles imply that he's related to the reptilian alligator. But his powerful neck muscles are arranged in patterns reflecting a different family of animals, the birds. The muscles indicate that T-Rex grabbed and pulled at its food like a carnivorous bird, pointing to the fact that birds are T-Rex's true modern cousins. 65 million years ago, the crocodilians weren't alone in surviving the meteor strike that wiped out the giant dinosaurs.
It took out all of the large species of dinosaur, but their lineage continues in the form of birds. The bird-type dinosaurs survived, and they're here now, flying around with us.
So what else can this bird connection reveal about the true nature of T-Rex? In Oblenis Hospital, Ohio, Dr. Larry Witmer is monitoring a unique patient. He's spent years trying to get into T-Rex's head, using the latest medical scanning technology to conduct a virtual dissection.
In the past, when we tried to understand T-Rex and we were looking at the fossils, we could learn only so much from the outside. But with the advent of CT scanning, it allowed us to peer inside to see what was going on.
The CT scan detects fractional differences in densities of the rock. Larry uses them to create a 3D model of the inside of the skull.
When we CT scan a T-Rex brain case, we can see where the brain used to be. We have a cast, if you will, or a mold of what the brain structure was like.
The scan is so detailed, it can register every tiny indentation on the interior walls, allowing Larry to produce something incredible, the precise shape of T-Rex's brain. At first glance, its size seems to confirm the dinosaur's pea-brained reputation.
You look at a brain like this, and it just seems tiny compared to the skull of T-Rex.
But this is not a problem, because bird brains are special.
Bird brain used to be an insult. Now it's actually a compliment. We've gotten new ideas lately on what brain size might actually be. So if we look at something like this and compare it to another brain, this brain right here, which seems so much smaller, is actually the brain of a crow. What we've discovered is that the brains of birds have a different arrangement of neurons than what we do as mammals. The neurons are much smaller and densely packed. And so in a sense, this brain that seems so small, a bird brain, is actually a very impressive cognitive tool.
But what else can we learn from the physical shape of a reconstructed brain?
When a lot of people look at T-Rex, what they see is a feeding machine. When I look at the head of T-Rex, I see a gigantic sensory organ. I see really the senses of a predator.
Larry has identified key regions associated with smell, sight, and hearing, and found they're supersized.
The olfactory bulbs are larger than what we see in really other kinds of predatory dinosaurs. That means it has a remarkably large sense of smell. So with regard to vision, we can look at the optic nerves that are bringing information in from the retina of the eye. And those optic nerves are really large, and that suggests to us that there was a really highly developed sense of vision that was very important to these animals.
But was he more hunter than scavenger? Another tiny structure provides a clue.
One of the things that can give us a view potentially at the agility of an extinct animal like T-Rex is the inner ear, the delicate canals that we call the semicircular canals. And that inner ear is sort of this delicate gyroscope that allows T-Rex to actually keep its eyes fixed on its prey as it's moving through space.
T-Rex shares this visual adaptation with cheetahs and birds of prey, predators that actively pursue their victims. Clearly, T-Rex was built for the hunt. But what else does its reptilian bird nature imply? Could T-Rex really have roared? The most chilling noises in the natural world today come from the top predators. The howl of the wolf, the roars of the big cats. But T-Rex's physiology leads experts to believe it sounded nothing like them.
If we look at any of the classic dinosaur movies, T-Rex is roaring. And the reason we probably thought of this as appropriate is that large carnivores today, most of them are mammals, and those are sounds that they produce. But when we think about T-Rex, this is an animal most closely related to birds and alligators and crocodiles. And those animals make very different kinds of sounds.
Trodden the footsteps of Joseph Goebbels.
Dinosaur vocalization expert Julia Clark and naturalist Chris Packham are teaming up to conduct a world-first experiment, recreating T-Rex's voice.
When it comes to understanding the physiology, the anatomy, and therefore the behavior and ecology of ancient animals, making comparisons with contemporary species is incredibly important. Julia, I rather perversely like the fact that T-Rex couldn't roar.
I know, it's really, you know, it grabs you and says, it makes you think, what was this animal really like?
The answer may lie with T-Rex's modern relatives, the birds and reptiles. Many of them communicate with a technique known as closed-mouth vocalization. Avian expert Chris suggests they begin the experiment with the typical closed-mouth caller, the Eurasian bittern.
They produce these very low sounds, booming, we call it.
Well, let's see how low frequency they really are, because they're not that large, but they're making a low frequency sound. So, Fabian, take it away. Can we make it louder?
Yeah.
I can see that being eerie in an English countryside.
Misty.
Misty.
Reeds, early morning or at night.
It's a little creepy. Even though it sounds really low to us, like
It's not that low, is it?
It's not that low. And so what we're talking about when we talk about what T-Rex would have produced or could have produced...
This is nothing. It's
this
much
is nothing.
lower than this.
Exactly.
The largest living birds, like the ostrich, make the deepest calls. But they're still only a fraction of the size of a T-Rex. So to make the sound of the biggest bird possible, they artificially drop the bittern call by 2 octaves.
All right,
Okay.
crank it. It seems subtle, but you know, it's deep.
Yeah.
I can barely hear it.
But deep doesn't necessarily mean quiet.
No.
But T-Rex's reconstructed brain is making Larry Witmer believe they should crank the bass down further, because the preserved inner ear provides clues to the key sound this beast evolved to hear: the call of other T-Rexes.
We can get some of that information by looking at the hearing organ, or the cochlear duct. What that suggests in T-Rex is that it was especially sensitive to low-frequency sounds, potentially frequencies lower than even most of us can hear, what we might call infrasound.
Modern animals use infrasonic sounds to communicate with each other across vast distances. Elephant rumbles traveled miles. Blue whale song can be heard across entire oceans. But amongst T-Rex's living relatives, only crocodilians share this infrasonic vocal ability. So the team now choose to experiment with an alligator call.
So what does it sound like if we take the Chinese alligator and we now move it a couple of octaves lower?
If we move it 3 octaves lower, it sounds like this.
Can we get it a little louder?
Just crank the fader, please.
Okay.
That's ominous.
That is very ominous. What I really like, Julia, is that this could be the first time for 66 million years that this sound has been heard on Earth.
It is pretty incredible.
I mean, it's a shot in the dark,
yeah.
But we are using the evidence that we've got.
If it sounds like this, I mean, I feel like this just induces fear. You know, I think that people think you need to have a roar for something to be really scary. But isn't that the scariest sound that you've heard?
Well, it's the scariest sound that I've felt. That's the thing, isn't it?
Yeah.
Tristan's rediscovered brain proves he was a beast primed for the hunt. His reptilian bird physiology indicates that he rumbled, not roared. But how did he catch his prey? Was he a lumbering lizard or an athletic assassin?
Tyrannosaurus, king of the tyrant lizards. 20 feet high, fiercest creature that ever lived.
For decades, this was how we imagined T-Rex, an upright lizard with a dragging tail.
With 6-inch daggers for teeth, he was the terror of his neighborhood.
But did the king of the dinosaurs really have such a regal bearing? In Dino Valley State Park in Texas, there lies an extraordinary set of ancient footprints made by dinosaurs very similar to T-Rex. Glenn Kubin has spent years tracing their tracks.
About 112 million years ago, this was not a riverbed. This was an ancient giant mud flat, and when the tide would go out, it would expose many miles of moist mud. When the surface is moist, like after a rain, it looks like they walked through 5 minutes ago. And to me, it's the next best thing to being beside a living, breathing dinosaur.
These trackways contain many clues as to how T-Rex would have walked around. The footprints are incredibly clear. But what's most revealing is the absence of the tail prints.
You see the 3 long, sharp claws, which is typical for a theropod. But there's no sign of a tail drag here or on any of the other trackways in the park, so we can be confident they did not drag their tails.
Trackways prove that Tyrannosaur-type dinosaurs clearly lifted their tails clear of the ground. This is evidence that T-Rex didn't stand tall. Instead, he bent forwards. his enormous tail balancing the weight of his enormous head. So, can these trackways tell us exactly how T-Rex moved? Studying the footprints with a combination of modern and traditional techniques, Glenn can reveal more than a dinosaur's shoe size.
We can tell, especially by the deeper tracks, that they would impress their toes and then pull them backwards and then go forward. They didn't push them forward because the front of the deeper tracks are not distorted. In most cases, they're walking at a normal pace and they're walking on their toes. And they look a lot like a large bird track.
So, would T-Rex have moved like a bird? Evidence from a team at the University of Chile provides clues about T-Rex's gait. By strapping a makeshift tail to a chicken's backside, these imaginative scientists are able to show that the bird's posture and bearing are totally transformed. It begins swinging its legs from the hip rather than the knee. This shows how a tailed T-Rex may have walked, but the bigger question is, could it run? The three-toed footprints on dinosaur trackways mirror those of modern flightless birds. Giant emus and ostriches might prove more useful models for T-Rex than the humble chicken. And these long-legged creatures are some of the fastest land animals on Earth. At full pelt, a flightless bird can exceed 50 kilometers an hour. So could the bird-like T-Rex have matched their speeds? In a lab in England, biomechanic expert John Hutchinson is putting all the evidence together to crack this puzzle.
The fossil footprints of a large dinosaur are really useful, but they only tell us so much. So we use experiments with living animals like an ostrich. We can go look at an ostrich, see how an ostrich moves, apply that information to the fossil record, using computer models to help inform us about how T-Rex might have moved.
One mystery that's been solved is the role played by his enormous tail.
By far the biggest difference between what we'd see in something like an emu and a T-Rex is that in a T-Rex there's a big muscle running from the tail to the thigh that powers locomotion, just like in a lizard or a crocodile.
T-Rex's tail muscle was integral in generating the enormous force necessary to power his legs at speed. But John calculates that with great power came great instability. Something best illustrated by dressing Tristan for a run. Let's bring Tristan up to 16 kilometers an hour, the speed of a jogging human. No problem. His flexing tail muscle helps his legs power along at a steady pace. But what happens if we push him up to emu speed, 48 kilometers per hour? His powerful muscles theoretically allow him to hit these speeds, but he's putting his life into his tiny hands. His pounding joints are now stressed to the limit. The slightest stumble could prove fatal.
The bigger you are, the harder you fall. So a 7-ton T-Rex falling down would hurt itself, and that would be maybe the end of it. So it'd be something a T-Rex would try to avoid actively.
So forget ostrich speeds. Tristan could barely outrun a human. And this does make sense. He didn't need to move faster. He just needed to be fast enough to catch his prey, those lumbering herbivores of the Cretaceous world. Tristan the T-Rex is coming together nicely. We've fleshed him out, road tested him, and given him voice. Now it's time for some beauty treatment. An animal's external appearance is a reflection of its biology, environment, and social world. So what should Tristan look like? The first step is easy. His reptilian and bird-like nature means we should coat his body in scaly skin. But what about color?
Many contemporary reptiles can be quite striking. If we think of things like coral snakes, which are red and yellow and black, and there are other reptiles, lizard species, which are blue and yellow. So there is, of course, some chance that T-Rex could have been quite brightly colored.
But doesn't a predator need camouflage?
If you're hunting in a dappled forest, then stripes might be the answer. Effectively, you might look like a tiger.
Or maybe we should be going with spots, like a leopard. Some think a large predator like T-Rex would need to hide in the shadows of the night, calling for a very different color scheme.
If you're hunting at night, then color itself can be largely unimportant because your prey is probably looking at you in black and white and vice versa. So therefore, it's all about tone and texture. Think badger, think raccoon.
This speculation, unfortunately, has its limits. But could there be another way that science can crack the mystery? In a lab in Austin, Texas, Julia Clark analyzes tiny samples from dinosaur fossils to try to determine their original color.
Like that one is what? It's about 1.5.
Using an electron microscope, Julia searches for hidden information, telltale traces of surviving pigments. And it's not looking good for a brightly colored T-Rex.
There are many pigments that are used in nature, and some of these pigments create very bright colors. But we don't have any evidence at present of them in the dinosaur fossil record.
Because I know parts of this animal.
What she has discovered are remains of structures that produce melanin, the same pigment that gives us freckles or a tan. Meaning one group of T-Rex's living relatives could provide a perfect color template. The birds of prey.
What we can say is that living birds that are meat eaters, that are carnivores of some kind, have an ecology that's somewhat similar at a very different scale from T-Rex, and they do not tend to be brightly colored.
According to Julia's research, the evidence is that T-Rex's predatory lifestyle puts his coloration squarely in line with these contemporary birds.
I think the T-Rex would have been colored in a palette of browns, blacks, maybe lighter tones, grays even, and that these colors would have been distributed in patches over the body, maybe breaking up the body outline, potentially serving in camouflage, but also parts of the body that might be a little more dramatic.
Color is often more intense around the eyes. Intriguingly, on T-Rex fossils, the eye region is dominated by suggestive bony structures.
So we look at the skull and we see these area of roughening that were almost certainly associated with fleshy display structures, and so they may have well used those for color, for what could be courtship signs. These were the kinds of social cues that T-Rex would have used to interact with other members of the same species.
So, following Julia and Larry's findings, we can give color to Tristan. Melanin tones and patterning for the body. And a touch of melanic orange around his eyes. Looking good. But if we're using birds as a guide, surely there's something we've forgotten. Wouldn't Tristan be covered in feathers? wouldn't be the first feathered dinosaur. Feathers evolved directly from reptilian scales.
Before T-Rex even lived, there were feathered dinosaurs, proper dinosaurs, but with feathers. Now, given we know that there are parallels in its skeleton, in other aspects of its anatomy, perhaps T-Rex would have been feathered too.
One of the first feathered dinosaurs was Archaeopteryx. Chris and Julia are examining one of its feathers.
All right, so you have to look at this. So this is 149 million years old.
It looks like it was pressed there yesterday.
Absolutely. So you see the center part, or the rachis, and then branches, which are the barbs, and then what locks it together tightly are these barbules that have tiny hooklets that lock the feather into form.
Just like a modern bird, and yet this is 149 million years old. And what color? Can you tell what color that feather was?
Well, another group's looked at the fossilized melanosomes in this feather, and they're consistent with a pretty dark tone. So maybe like a black, or there could be some gradations in black, some subtle tonalities, but overall quite dark in color.
And these feathers clearly evolved millions of years before T-Rex.
Absolutely.
So could T-Rex have had feathers like this?
Well, the short answer is no.
Right.
T-Rex didn't evolve from flying dinosaurs. Yet recent digs in China have uncovered some of his relatives. They prove that Tyrannosaurs did indeed have a simple form of feathering.
From what we know from other tyrannosaurid dinosaurs, T-Rex had modified feathers. Not in the sense that they were bird feathers, but modified feathers.
Like the filaments on the face of today's flightless birds.
So if we look at this cassowary that's been checking us out, these are much more simple bristle structures. They're like the center part of the feather, but without any branching structures to the side. So here they're big, stiff structures that are on the wing of this cassowary, which is really tiny. But even around the face, we can see simple structures here under the beak, and even kind of in the eyebrow zone above that are like single filaments. And that's what we find in relatives of T-Rex from China.
So what does this mean for Tristan's splendid plumage? Well, complex feathers are definitely out. And as a large, warm-blooded animal, he has little need for insulation. So he probably just sports a sparse sprinkling of those spiny tyrannosaur bristles. What an attractive specimen. He's now almost complete. But to accurately reflect the true T-Rex, is there anything we should know about his social life? Startling evidence for Tyrannosaur's social structure is buried in this landscape. In the wilds of these Alberta Badlands, a collection of game-changing bones were uncovered by paleontologist Phil Curry. The fossilized remains of 26 Albertosaurs, close relatives of T-Rex, lying together in a group.
The indications are very clear in this bone bed that the Tyrannosaurs were here because they died together at the same time and almost certainly were living together up to the time of their death.
Until this find, Tyrannosaurs were thought to be lone rangers. But the discovery gave strength to the idea that instead, they existed in family groups.
The smallest animal we have in here was about 2 years old, and the largest animal was about 24 years old.
When you start finding juvenile animals that are living with a large number of adults, then you have to start thinking about family structure in these things.
We don't really know what's happening with the Tyrannosaurs. We do know that this is almost certainly a pack. And I just think it makes perfect sense that if these animals were moving together, that in fact they were hunting cooperatively.
Today, pack predators are not unusual. The African lion lives and hunts in a family unit, the pride. This social lifestyle provides protection, childcare, and numerous opportunities for mating. But males also fight for dominance, often causing deep facial wounds. Tantalizingly, many adult T-Rex skulls show similar scarring.
These animals were actually biting each other in the face, and we know that it must have been T-Rex because nobody else is biting T-Rex in the face other than another T-Rex. These face-biting behaviors may have been part of the mating rituals for these animals. We don't really know for sure. One thing we do know is that features like these scars on their faces show that these animals were interacting with each other in routine and regular ways, because we see lots of them.
It's almost universal. It's not a matter of just 1 in 30 animals does this. It's just about all of the animals that we find will have tooth marks somewhere on their jaws. And so this seems to be something that tyrannosaurs were doing often. And it's something that happens with modern animals as well.
And that's not all. Evidence from the shape of his brain also appears to support the idea that T-Rex was a social animal.
When we look at the brain of T-Rex, we can't really see direct signs of sociality. There's no social lobe that we can see on the brain. But we can see that the cerebral hemispheres, those parts of the brain that are associated with higher cognitive functions, with problem solving and creative thinking, if you will, were actually large enough in T-Rex that sociality might have been absolutely possible.
We're getting more and more evidence all the time, and I don't think it's something that we can deny anymore. Whether we're talking about herbivorous dinosaurs or carnivorous dinosaurs, these things were a lot more socially complex than we ever imagined.
But the true advantage to living in groups comes with the hunt. And Phil believes this is another example where lions may provide insight into the social life of tyrannosaurs.
Very often what happens, it's the young lions and lionesses that are the ones that do most of the hunting. They do the running. Very often what they'll do is they'll chase the herbivore back towards the jaws of the adults, the ones that have the real power.
T-Rex packs had an extra weapon in their arsenal, their fast-moving young. We know this because the bones of juveniles show them to be markedly different to the adults.
The juvenile animals would have had very long legs. It would have been very lightly built. It would have been fast and agile. Even its jaws are very slender, and its teeth are quite small compared to the size of the animal.
Juvenile T-Rex's appearance is so different to the adult that until a few decades ago, experts thought they were different species. In his lab in Florida, Greg Erickson has been investigating the secrets of this transformation. By slicing through fossilized T-Rex bones, he's revealed their annular growth rings.
Aging a dinosaur like Tyrannosaurus rex is very much like aging a tree. Dinosaurs put down annual growth lines. You can see some of them here. And simply by counting up the total, we can figure out how old an animal was at the time of death.
But the rings also reveal that at about 12 years of age, T-Rex began the mother of all teenage growth spurts. The increase in the gaps between rings indicates that in just a few years, T-Rex grew 3 times in height and 6 times in weight.
In its teenage years here, this animal was putting on about 5 pounds of weight per day. It's mind-boggling.
Tyrannosaurs went through an incredibly fast growth during their teenage years. These animals would have changed from one form of animal into another over a very short time.
The extreme growth allowed the adult T-Rex to obtain its defining weapons. Those almighty jaws with their bone-crushing teeth. Which explains its extraordinarily tiny front limbs. They have remained the arms of a child. If T-Rex did in fact live in social groups like today's lions, then we should add some final touches to Tristan's appearance. Fights with other males would have covered his face in scars. And under pressure to attract females, he may have adapted his bristles for social display.
Now, if they've got to be there, why not use them for a purpose? And when you think of contemporary animals, such as lions, the males use them as a mane. And we know full well that the bigger and blacker the mane, the more attractive that lion is to a female. I imagine a maned T-Rex is a real possibility.
A bristly crown for the king of the dinosaurs. After 65 million years, Tristan is whole again. It's time to set him free.
As time goes on, we're finding more and more things about Tyrannosaurus rex that suggest that this is an animal that deserves its reputation.
It's gone from a tail-dragging dullard to a fast-moving super predator, one of the planet's most magnificent animals ever. What a transformation.
Science has really started to flesh out what T-Rex was like. Its secrets are now being revealed.
It's something that seems as if it could come from a nightmare, but it is truly part of the same biological world that we are. It adds to our understanding of what comprises biodiversity on Earth.
Once you start delving into the details, you realize just how sophisticated this dinosaur was. It was so awesome in so many ways.